All right, good morning. Wow, packed house. Okay, so what I'm going to talk to you today is about a series of techniques that are good at taming tail latencies in large online systems. So why do we care about this? Well, first of all, if you can make your web applications perform in a more interactive manner, they feel a lot more fluid and natural, and users have a better experience. But it's actually pretty challenging to do the amount of work you need to do to reconstruct a search page on every keystroke of the user. So the reason that is that when a query comes in, there's a whole bunch of subsystems that need to be used in order to generate the information we need on the search results page. So we break these large systems down into a bunch of subservices, and we need enough computational power on the backends that we have to take a query in, and it eventually hits thousands of computers. And we need to get all the results back and then sort of decide what we're going to show to the user in a pretty short amount of time. So one of the things about Google is that all of these services run on a shared environment. So we're not dedicating machines to particular subsystems within our online services. We're instead running them in a big pool of machines where all kinds of different things can happen. You can have network congestion because some other service is using the network that you wanted to use. You can have background activities on the same machine. Some other task on the machine can crop up and suddenly spike and use lots of CPU cores that you wanted to use. So in general, shared environments are great because you get much better utilization out of your hardware, but they're really hard to predict effects that arise from doing this. And it's exacerbated when you have these large fan-out systems because the more machines you touch, the more likely it is that something unexpected will happen. So I don't often get to use my vacation photos, but so what happens when you look at your own software? It normally looks really fast. That looks fast, doesn't it? So the problem is when you inspect the latency of your software when running under a shared environment, you discover it has a very long tail. So to drive that point home, if you have a server whose average response time is 10 milliseconds, so pretty fast, but the 1 second 99th percentile latency, if you only have to touch one of those, then 1% of your requests are going to take more than a second, but most of them will be pretty fast. But if you need to touch 100 of these and get back responses from all of them, then 63% of your requests are going to take more than a second because at least one of those servers will generally be in the long latency regime. Okay, so just to illustrate the shared environment that we tend to operate in, all of our data center machines run Linux. On top of that, we run a bunch of system-level services like a file system, chunk server, scheduling system to start up tasks and stop them, various other system services, mostly kind of sitting there in the background, compressing logs and doing various other things like that. And then we run a bunch of application-level services and other kind of higher-level system services. So we run often big table tablet servers for our distributed storage system. We might run some CPU-intensive job sitting there, doing something in the background, some random MapReduce that some other team is running, and a bunch of other random things. So this is kind of the application environment in which your software is running. So in order to reduce latency, I'm going to talk to you about a few techniques we've discovered that allow us to sort of really rein in the long tail of latency without increasing the performance cost of the system too much. So there's a bunch of kind of just basic hygiene things that you like to do when you're trying to build low latency services. So these are just generally good ideas. You're probably already doing a lot of these things, but I'll just go over them quickly. And then I'll talk about some techniques in distributed systems that are particularly useful for where these cases are, where these techniques are not enough. So one of the things you want to do is have differentiated services classes. So if you have sort of interactive requests and kind of background requests, you really want to prioritize the interactive ones and not only do the background ones when you know you're not really going to be affecting real users waiting for things. And same thing with your network traffic. You want to prioritize traffic related to interactive requests much higher than any sort of background push activities or anything like that. Sometimes in your systems you can end up with head-of-line blocking. So if you're trying to read a 16 megabyte chunk of data from disk, and meanwhile queued behind that is a 100 kilobyte read that's needed for some user request, you really want to break that 16 megabyte read into a bunch of little smaller ones and allow the 100 kilobyte one to slip in the middle so that it doesn't sort of spend a really long time waiting for that big request. And often in your systems, you have these complicated and expensive background activities that are going on that aren't sort of essential to do right then, but you can kind of choose to do them at reasonable intervals, and you have a bit of flexibility in when to do that. So you want to kind of rate limit that kind of activity, and you can also defer that kind of activity until you have a better opportunity to do it when the load is lower or at night or other kinds of things like that. Okay, so these are just kind of basic hygiene. Everyone's probably already doing these things. I will not dwell on those further. Okay, so I'm going to make an analogy to tolerating variability with fault tolerance. So fault tolerance is typically a hardware technique where you use extra resources that are inherently unreliable in and of themselves as building blocks, but you use them in ways that you can, from these unreliable pieces, make a reliable whole. So by analogy, we'd like to be able to use unpredictable and sort of highly varying latency pieces in our system, but collectively we'd like to make a predictable whole out of the unpredictable parts. Now, where the analogy breaks down a little bit is that the time scales of what you have to do are very different. So in fault tolerance, you're really worried about things like a hard drive crashing or the machine's power supply crapping out and you having to deal with that. And that doesn't happen that often. That's kind of like tens of events per day, hundreds of events per day. When you're trying to tolerate variability, these kinds of things happen thousands of times per second in your data center. So you really need to be able to react much more quickly to variable events, variable latency events, than you do to real actual hardware failures. But it's not a bad analogy. You're essentially trying to use unpredictable things to make predictable things. Okay. So I'm going to break these latency tolerating techniques into two classes. The first is what I'm going to call cross-request adaptation. And those, you're essentially examining the recent behavior of your system, collecting a bunch of statistics, looking at latencies, looking at how different backends are performing, and then you're going to take some action to improve the latency of future requests, typically relating to load balancing or managing the load across a whole bunch of servers in some way. And the time scale for these kinds of actions is generally tens of seconds, maybe minutes. It's not kind of many times per second. And then the second category that I'll talk about is within request adaptation. So essentially, you want to cope with some slow piece of your subsystem in your overall system in the context of a higher level request. A user issued a query, some subsystem is being really slow, and we want to do something about that right now while the user's waiting so we can get them their response faster. Okay, so the first thing that's useful is to do fine-grained and dynamic partitioning. So in some systems where you have n machines, you could just say, well, I'm going to partition what my system needs to deal with into n pieces, give each one of those machines one of those pieces of work, and be done with it, and just kind of live with whatever latency you get. That might work reasonably well if you know you can partition them into totally equal pieces and that you don't have any other shared environment kinds of activities going on those machines. But once you have shared environments, the load on the machines is kind of inherently unpredictable. It's not really under control of your application alone. It's kind of whatever else the system decides to run on those machines can suddenly cause a machine that was underloaded to suddenly become overloaded. So one of the techniques we often use in a lot of our systems is that we want to partition these large data sets or computations into a bunch of pieces, more than one piece per machine, usually 10 to 100 per machine, actually. Our big table system does this. Our query serving systems do this. GFS does this by taking large files and breaking them into 64 megabyte chunks. And the reason you want to do this is that a few reasons, actually. One is that it's very good for load balancing. So I can actually shed load in a few percent increments if I have between 10 and 100 pieces of work per machine. So if this first machine gets overloaded, I can say, well, I'm going to pick one of the pieces of work I'd assigned it and move that to some other machine. And now all of a sudden the load on that machine drops a little bit, and the load on the other machine rises a little bit. So you can do very fine-grained load balancing in this way. The second reason to do this is it really speeds failure recovery. So in essence, if you have n pieces of work assigned to a machine, recovery can happen with n-way parallelism. So if this machine dies, now we have to make the system whole again. We need to sort of reassign whatever it was responsible for to other machines. And we can do that in such a way that each of them gets assigned one piece of work. It does whatever computation it needs to kind of bring up that piece of state and start serving it. And if you had 100 pieces of work, you have 100-way parallelism on that recovery. And so recovery can actually be very fast in these kinds of circumstances. Another technique we often use with these fine-grained partitioned objects is selective replication. So we can find heavily used pieces of the data or computation and make more replicas of this. And this can either be static or dynamic. So in our query serving system, for example, we make more replicas of important documents. That we do because they're also, the important ones also tend to be more expensive to score, so you have kind of load imbalance from that. But also, the more important ones, it's bad if your system suddenly stops serving the CNN homepage as a query result for any period of time. So by having multiple replicas of that, you actually help avoid that. You can also do this dynamically where you, for example, as Chinese language query traffic load increases, you start making more replicas of the pieces of data containing Chinese documents. And then as that load drops off, you decrease the amount of replicas you use for that. Okay. Another thing we sometimes do is what I'll call latency-induced probation. Sounds like a horrible school treatment you might get. So servers are sometimes slow to respond, and that slowness in response could be data dependent. So it could be that there's just no two ways around it. That particular piece of data that system is serving is slow. But sometimes, perhaps even more often, it's due to interference effects. All of a sudden, something else on that machine is causing it to be slow. And so there's like a CPU spike on that server, and it just isn't able to keep up with the request load you're giving it for your particular application. So a somewhat non-intuitive thing to do is to actually remove that capacity when you're under load, and that actually can improve latency. So in particular, you can initiate corrective action. You can make copies of the data it was serving onto other servers, and you can then continue sending a shadow stream of requests to the original server that was having trouble and measuring the latency. But you're not actually waiting for that shadow stream to finish before you sort of finish the higher level processing you need for the user's requests. So you can keep measuring the latency, and then you can return that machine to service when the latency has gone back down and you're sort of convinced that whatever problem that machine or system had is now over. Okay. So all those techniques are good at kind of the time scale of 10 seconds, kind of a minute level kind of thing. Those are the cross-request adaptations. What I'm going to talk about now are techniques for within-request variability. And so in particular, we're going to take action within a single high-level request with the goal to reduce overall latency. And we don't want to increase our resource usage too much, and we will also want to keep our serving systems safe. We would prefer them not to crash. Okay, so one of the ways for keeping your serving systems safe in the presence of a large Fanout system. So normally you take in a query at the top of this tree, and you're going to send it down to the parents and then eventually to all the leaves, and there's thousands of leaves there. So what happens if all of a sudden your query parsing code that runs on the leaf seg faults for some reason? It's got that query has some weird property you've never seen before, and all your testing you've done hasn't really captured it. And all of a sudden you send the query down, and bad things happen. So that's kind of unfortunate. That will really drive up your latency latency concurrent requests to that data center. You've essentially killed your whole data center, your whole serving cluster. And it takes a while to bring back up all the processes and get them back up into a state where they can serve requests. So one of the techniques we've been using for years and years is what I'll call canary requests, with the analogy to the canary in the coal mine to tell miners that something bad's going to happen. So what we actually do is we take a little bit of a latency hit here in order to keep the serving system safe. So what we do is we send the query just to one leaf. And if that succeeds, then we have more confidence that that query is not going to cause trouble sending it to all 1,000 or several thousand servers. So at that point, then we can go ahead and send it to everyone else. Now, if on the other hand, that query that we sent to one leaf never returned, then we're a little suspicious. We might pick another leaf and try one more time. But we definitely don't want to send it to all 1,000. It's also a good idea at that point to record what the actual request was so that you can investigate why perhaps you're killing your backends with that. But once you have that confidence, then you can go ahead and send it to all the leaves and get your results back. Okay, backup requests. So remember, in these shared environments, little blips can happen at all times. You might have a system where you have a client of some subsystem, and you have a bunch of replicas. So you can pick any of these replicas to send a request to. It's some idempotent request. And there's your request. So you're going to pick replica 1. And it's going to go in a queue in replica 1. And unbeknownst to the client can't really tell how long the queues are in all the different backends very well, especially if there's lots of clients and lots of replicas. It's very hard to maintain very fine-grained state about exactly which replica has which queue length. And you don't really want to do another round trip to probe the queue lengths of a bunch of servers. So you send it to one of them, making your best decision about knowing whatever you know about the load on the backends, and you send it there. But then after a little while, you're going to send it there because you haven't heard back from replica 1. And so now you have your request in 2 places. Replica 2 actually is faster and manages to get to your request sooner. And so now you get your reply back. And then you can say, oh, by the way, don't worry about it. I'm done. Now, the problem with this is that, well, one of the good things about it is you actually will get much better latency by sending to 2 servers rather than 1, generally. The problem is you've pretty much gotten a pretty high chance of getting double the performance cost of doing that query. Because in the time it took to do request 9, the other server could have also started processing request 9. And you really, if these requests are expensive and you have capacity issues, you don't really want to pay that cost. But it does work pretty well at reducing latency. So let's look. So in this set of measurements, I took an in-memory big table service spread over 100 tablet servers. So there's 100 machines. We're going to do a fan out of a 100-way fan out to get the data for 1,000 keys, little values associated with the keys. And then we're going to measure the time for the whole round trip of all 1,000 values to come back. So if you don't do any backup requests, you see that the average is 33 milliseconds. This is on a loaded cluster doing all kinds of other stuff, so not the best you could do if you really cared about latency. But without any backups, what you see is your standard deviation and your 99 percentile, 99.9 percentile are pretty high. And that happens because Bigtable might have decided to move a tablet. And so during that brief period, that tablet is kind of inaccessible, and you have to kind of wait for it to be loaded back up on another system. On the other hand, if you have another copy of that data, and you could issue a request to that other table, and you can issue backup requests for any keys that are still missing after 10 milliseconds. What you see is that you dramatically bring in the latency tail of those requests, of the time for getting all 1,000 keys back. And even backup after 50 milliseconds does a pretty good job of controlling the really hot long tail. And you actually have a pretty modest request load increase. And the reason for that is that after 10 milliseconds, most of the keys are back. So it's not like you're sending out for all the keys. It's just a few stragglers that you're trying to deal with. Okay. So now let's talk about a slight variation of this technique that we use in our distributed file system. So I gave it the name backup request with cross-server cancellation. It's not a very inspired name, but too bad. Okay. So what we're doing now is we have, again, a couple of replicas we could choose to send a request to. And so the client's going to pick one. And when it does that, it's going to tag that request with the identity of other servers it might decide to send the request to. So when it sends to server 1, it says, oh, by the way, here's request 9, and I might also send this request to server 2. And then very soon after, much sooner than when it thinks it should get results back, it's going to send the same request to server 2 with the identity of server 1. So now we have a little race going on, right? Who can satisfy my request first? And let's say server 2 manages to do this. So when server 2 starts processing the request, it's going to send a little sideways message. And it says, hey, this is server 2. By the way, I'm starting on request 9, so don't worry about it. I've got it. So at that point, the latency variability on server 2 is much reduced because you're no longer waiting for requests ahead of you in the queue. You know you're about to start processing that request. Now, you could still get some sort of blip, but the probability of that is much reduced. And so now, server 1 has a few different things he can do. In this case, he's just decided, fine, I'm going to let server 2 deal with it. I'm just going to drop this request on the floor and ignore it. And now server 2 finishes that request, sends a reply to the client. Client's happy. Okay. So there's a bad case. Everyone see what the bad case is? Yeah. If they get to the request at about the same time, then like ships passing in the night, they both do this. Now you can check again when you finish the work to see if that situation happened and only send one copy of the reply. But you do double the work in this case. But it's a fairly small race. And as network latencies go down, the probability of that race decreases. Okay. So we implemented this in the context of our distributed file system. So typically we have 3 places we can go to get any particular chunk of a file. And the way we implemented it is we pick one of them. We send the request to that replica. We wait 2 milliseconds, which is generally faster than you might expect to get data back from your file system, especially if it has to do a seek. And then we're going to just go ahead and send the request to the second replica. And that servers do this cross-server cancellation thing. And then we measure the time for big table monitoring ops. So this is through a much bigger, complicated distributed system of how long those monitoring ops take to go from a client monitoring app through a big table server, eventually down to the distributed file system, do the read, get the data back out of big table. So it's actually not just the file system latency, but sort of the latency, end-to-end latency of these monitoring apps. Okay, so if we take a mostly idle cluster and we use the original policy of no backups, we just send the request to one place and wait, then that's the latency distribution we get. But if we send the backup after 2 milliseconds, you see the latency tail, especially, is dragged in a lot. The 50th percentile goes down a bit, but the 99th percentile, 99.9 percentile go down quite substantially, which is nice. And this was on a mostly idle cluster, so there was pretty much nothing else happening on the cluster except for my big table servers and the disk servers. So now we're going to do the same measurement, except we're going to be running an enormous MapReduce that's sorting many terabytes of data. So that's essentially saturating the CPUs and the network and all kinds of other stuff in our shared environment. And what you see is that, first of all the latencies are higher because there's other stuff going on. But you see that the same kind of effect happens. You're able to control your latency much better by having these backup requests. So we get almost the same reduction in latency tail. And you're only doing about 1% extra disk reads, which is quite nice. Because most of the time, the cross-server cancellation actually is successful, and those cross-server messages are tiny UDP packets. It's very cheap to actually do the sort of synchronization and the communication about who's doing what relative to disk reads. So now, if you squint at these lines, look at those latency profiles. Those are actually remarkably similar. So essentially, if you don't do backup requests, you have to keep your cluster pretty idle to get that kind of latency response. If you do backup requests, you can run a huge, enormous background batch processing job and still get the same latency profile for your interactive requests. That's pretty nice, because you kind of got a cluster for free in some sense. And there's a whole bunch of variants that are possible in this system. You could send to a third replica after a little bit longer delay. Turns out sending to 2 gives you almost all the benefit. You could keep requests in the other queue rather than deleting them entirely and just reduce the priority so that if the other disk server has available spindle time, it can go ahead and do the read even if there's a chance it might do double reads. You can handle Reed-Solomon reconstruction similarly, although it's more complicated. Okay. So, in conclusion, techniques like these are really good at helping you tolerate variability in your systems. And if you run in any sort of shared environment, you're going to have variability that isn't really in your control. There's other little things going on in the system. There's other people trying to use the network you're trying to use. There's other applications spiking and using CPU that you wanted to use. So you really need to build your systems that can tolerate variability and latency using higher level techniques like these. Obviously, you should do all the techniques within a single process that you can do to make your latency less variable. But once you've done that, it's kind of untenable to stamp out all sources of variability in shared environments. So you really need these latency toleration techniques like these to really get things to work well in a shared environment. And it's a bunch of different things. It's the good engineering practices I described first. And then these cross-request adaptations allow you to do kind of adaptation at the 1 minute, 10-second, kind of few-minute level. And then the within-request adaptations are actually quite effective at controlling tail latency in these shared environments. So I'll point out this is joint work with my colleague, Luis Barroso. We wrote an CACM paper about this a while back. And many other people at Google have contributed to this work. I'll be having office hours today at 10:45, booth 801. So thank you very much. Appreciate it.